You've watched it 100 times without ever really watching it. A road roller crawls across fresh black asphalt on a summer afternoon. Big drum out front, big drum behind, driver looks half asleep. The whole machine moves at the speed of someone slowly making a decision. It's the most boring vehicle on the entire construction site. You drive past it on your commute. You wait at the flagger because of it, and you never wonder what it's actually doing. But have you ever stood close to one? Close enough to feel the ground shake under your feet from 20 feet away? Because that drum isn't just rolling, it's vibrating violently the entire time, slamming the road thousands of times a minute with a force you can feel through the soles of your shoes. So what is it actually doing? Is that just engine vibration shaking loose? Is the operator getting rattled half to death on purpose? And why does a machine designed to flatten something need to shake it all? The answer isn't it presses the road flat. That's the surface answer, and it misses almost everything. The real answer involves 160 years of engineering history, a temperature window measured in minutes, and a piece of physics that also explains why a jar of mixed nuts settles when you tap it. By the end of this, you'll never look at a road roller the same way again, and the connection to your daily life is bigger than you think. You've been walking on the result of this every single day without noticing. But let's start with what everyone gets wrong about that drum. The obvious answer is the wrong answer. But it's only wrong by a degree. Most people, if you ask them, would say a road roller works because it's heavy. The drum is huge, the machine weighs 10 to 15 tons, and gravity does the rest. Press down hard enough and the asphalt squishes flat. Simple. And here's the thing, that's not wrong. Weight matters. But weight alone is genuinely terrible at compacting a road, and engineers learned this the hard way over a period of about 90 years. The early steamrollers from the 1860s, the ones Thomas Aveling pioneered in Kent, England, weighed around 30 tons. They were monsters. And those monsters still needed 8, 10, sometimes 12 passes over the same strip of road to get it close to dense. And close to dense was the best they could do. The result was a road surface that looked smooth but had air voids hidden inside the mix, tiny pockets where the asphalt particles never quite locked together. Here's what nobody mentions. Granular materials like the aggregate inside hot asphalt physically resist being squeezed flat by pure weight. The particles wedge against each other and hold the load like a stubborn arch. You can sit a 30-ton weight on top of them and they'll simply support it. They won't rearrange. They won't get denser. They'll just take the load. The only way to break that stubborn arch is to make the particles let go of each other for a fraction of a second so gravity can pull them into a tighter pack. And the way you do that is by vibrating them. So inside a modern road roller drum, there's something most people never even consider. A spinning, unbalanced weight. An eccentric mass. Sometimes two of them. They're driven by hydraulic motors. They spin between roughly 1,500 and 3,500 times per minute. And because the weight is unbalanced, every rotation throws the drum violently up and down, hammering the asphalt thousands of times a minute. That's where the dynamic force comes from. A drum that weighs 10 tons standing still can hit the road with the effective force of 40 or 50 tons when the vibration is engaged. Multipliers of 2 to 5 times the static weight are standard in manufacturer's specs. So the drum isn't pressing the road, it's pummeling it. And it's pummeling it at a tuned frequency that the operator can adjust on the fly. But that's still not the part that should surprise you, because the frequency of that vibration isn't random, it's tuned. And what it's tuned to is genuinely strange. The frequency is tuned to the material. Asphalt isn't a single substance, it's a mixture of stone, sand, filler, and binder. And that mixture has a specific frequency range where it accepts compaction efficiently. Run the drum too slow, and the energy doesn't transfer. The particles don't get jostled hard enough to rearrange. Run it too fast, and you crush the aggregate, fracturing the stones inside the mix and producing surface cracks the moment the road opens to traffic. The operator's amplitude switch controls how hard the drum hits. High amplitude, long throw, harder hit is for deep lifts of soil or thick asphalt layers. Low amplitude, short throw, gentler but faster is for thin surface layers where a hard hit would shatter the aggregate. Choosing wrong on a thin mat doesn't just produce a worse road, it destroys the mat. The operator is making this call in real time, and they're making it on a clock. Hot mix asphalt comes out of the truck at roughly 275 to 325 degrees Fahrenheit. It has to be compacted while it's still hot enough for the binder to flow, generally above 175 degrees. Below that, the binder stiffens. The particles seize in place and no amount of vibration can save the mat. The effective compaction window is commonly cited at 10 to 20 minutes, sometimes less on a cold day. So the operator isn't slow. The operator looks slow. The operator is actually racing a temperature gauge inside the asphalt that's dropping every second. And this connects to something sitting in your kitchen right now, the way a jar of mixed nuts or a bag of flour settles when you tap the bottom. Same physics. The vibration breaks the static friction between particles for a microsecond, and gravity does the rearranging. We'll get to that. But here's the part that genuinely surprises engineers when they see it for the first time. On modern rollers, the drum isn't just compacting the road, it's also reading it. Intelligent compaction technology, which FHWA has been pushing since the mid-2000s, puts accelerometers and GPS units on the drum. The drum bounces differently depending on how stiff the material below it is. Soft spot? The drum sinks slightly and the vibration response shifts. Hard spot? The drum bounces sharply and the response shifts the other way. The onboard computer translates this into a real-time stiffness map of the road. The operator can see on a screen exactly where the road is dense and where it isn't. Several state DOTs now allow or require it on major projects. The roller has become a controlled earthquake and a soil density sensor at the same time. The target air void percentage in finished asphalt is typically around 4 to 8%. Every percent off target shortens the road's life dramatically. Miss the window by enough and you've just built a 3-year road instead of a 20-year road. But none of this, the frequency tuning, the amplitude control, the temperature window, the real-time sensors, actually existed for the first 90 years of road building. So how on earth did we get here? Go back to the 1860s. Thomas Aveling, an English engineer in the town of Rochester in Kent, takes a steam-powered traction engine and adapts it for road work. His company, Aveling and Porter, founded in 1862, becomes the most famous name in road rolling for nearly a century. Their machines, those 30-ton steam-powered monsters with the rampant horse logo on the side, dominate British and American road construction for decades. But here's the brutal truth about that era. Nobody actually understood what compaction was. They knew rollers made roads smoother. They didn't know why some roads survived 10 winters and other roads, built the same way with the same equipment on the same kind of soil, failed in 2. The variable was invisible. And then, in 1933, a construction engineer named Ralph Proctor, working on water reservoir dams in Los Angeles, ran a series of experiments that quietly changed everything. He discovered that compaction wasn't just about force, it was about moisture. Every type of soil has an optimum moisture content, a specific water level where it accepts compaction most efficiently. Too dry and the particles won't slide. Too wet and the water itself takes the load instead of the soil. Proctor's test, still called the Proctor compaction test today, became the foundational quality control measurement in every road and dam project on Earth. Before Proctor, dam failures were so common that engineers genuinely did not know why their structures collapsed. After Proctor, they knew. And here's the surprise. Even with Proctor's insight, static rollers, the Aveling kind, were still the standard for another 20 plus years. The breakthrough came in West Germany in the 1950s. Bomag, founded in Boppard in 1957, was one of the companies that took an old idea, vibratory compaction had been experimented with in plate compactors, and engineered it into a full-sized road roller. The math changed overnight. What had taken 12 passes with a static roller could now be done in 4 with a vibratory machine, often with a lighter drum. Lighter, faster, more accurate, and producing denser roads. Within 20 years, vibratory technology was the global standard. Therefore, what you're watching when you see a modern roller crawl across hot asphalt isn't just a heavy machine. You're watching 160 years of accumulated engineering. Aveling's weight, Proctor's moisture, Bomag's vibration, and now intelligent compaction's onboard sensors, all working together in a single drum. And the place all of that engineering actually lands is somewhere you walk on every single day, somewhere you've already walked on this week. Here's the part that should make you slightly uncomfortable. You've been touching the output of this system your entire life and never connected it to the machine. Every road you've driven on today, the highway, the side streets, the on-ramp, was compacted by a vibratory roller in a temperature window measured in minutes by an operator racing the clock. The parking lot at the grocery store, your driveway, the pad your air conditioner sits on, The runway your last flight took off from, where compaction tolerances are even tighter because a poorly compacted runway joint can throw a 747 around. The railway bed under every freight train and every commuter line. The foundation of the building you're sitting in right now had its subgrade compacted by a vibratory machine before the concrete was poured. And here's the connection to something you actually complain about: potholes. Every pothole on your commute is a piece of forensic evidence. Either the operator missed the temperature window, or the amplitude was wrong for the lift thickness, or the moisture in the subgrade was off Proctor's curve, or the air void percentage came out too high and water got in over the first winter and froze and expanded and split the road apart. Potholes aren't random, they're a record. The American Society of Civil Engineers has graded American roads in the D range for years. Drivers in the U.S. collectively pay billions of dollars a year in vehicle damage attributable to poor road conditions. The country has roughly 4 million miles of public roads, and a meaningful chunk of the annual hundreds of billions spent on roadwork goes specifically toward fixing pavement that wasn't compacted to spec the first time. Compaction quality is one of the biggest hidden variables in the entire trillion-dollar infrastructure conversation. And here's the kicker. Asphalt is, by tonnage, the most recycled material in America. The country grinds it up, reheats it, and lays it again. And every time, that hot mix has to be compacted in the same impossible 15-minute window by the same slow-looking drum running at the same tune frequency. The roller isn't a background character. The roller is the difference between a road that lasts 20 years and a road that fails in 3. So here's where you actually land. You looked at that road roller on the construction site and saw the slowest, most boring machine in the lineup. A guy in a yellow vest, a big drum, a low rumble, a vehicle that moves at the speed of someone making a hard decision. You judged it. You waited at the flagger and you were mildly annoyed. But what you were actually looking at was a controlled earthquake running at a tuned frequency, a real-time density sensor mapping the road as it rolls, an operator racing a temperature gauge inside the asphalt with a window measured in minutes, 160 years of accumulated engineering from Avaling's 30-ton steamrollers to Proctor's 1933 moisture insight to Bomag's vibratory revolution in 1950s Germany, and the single piece of machinery that decides whether the ground under your feet holds for 2 decades or fails before your kids learn to drive. That slow drum is the reason your commute exists. Your runway holds a 747. Your driveway didn't crack last winter, and the foundation under the chair you're sitting in is still flat. You're not looking at a road roller. You're looking at the quietest gatekeeper of every paved surface in your life. And if you think a vibrating drum is the strange part of road construction, wait until we get into why fresh asphalt is sometimes laid down white and what that color is actually doing to the engineering underneath your tires.